Welcome to Hot Chips 22. The afternoon tutorial, Optical Interconnect.
In his last year as a PhD student working with Professor Karen Bergman, and his work is on photonic network design for many core CMPs, and he's been looking predominantly at software tools for CAD and simulation of photonic networks on chip and automating the device design and layout for various kinds of trade-offs of these networks. He's been working with various DARPA, DOE, NSF, all the standard players, and he'll talk about some hybrid data networks they've been looking at Columbia. So Gil?
Cool, thanks. There we go. Alrighty, so this talk is, again, sort of kind of focusing on future photonic network on chip design for about 10, 15 years down the road. And this is actually, if you were at Hot Interconnects, this is sort of a prequel to my talk there. So pretend like you didn't hear that, listen to this, and then remember that you heard that, sort of, I guess. So I think everyone here knows the problem. We have many, many cores coming on chip. We already see that today, and so how are they going to communicate? This is sort of our picture that we usually use for what we think it's going to look like. Whether you think it looks like this or not it's probably going to look similar, right? Where we have some cores, a lot of them on the bottom, and depending on the role that 3D stacking will play in future CMPs, we could see multiple layers of memory here, where we could have actually a lot of memory, depending on how much we can put on and if we can solve sort of the challenges of getting heat off the chip. And then possibly a separate layer or multiple separate layers for the interconnection network for both on and off chip. So I don't think I need to motivate why we want photonics either, even though we're hard at work making it sort of make sense in terms of cost and how we can integrate as much on chip or even on board as possible. It basically boils down to that it's cheaper in terms of energy for distance, basically, just like it is in telecom and elsewhere. And so what we kind of realized early on was that obviously optical processing or sort of implementing logic in the optics domain is sort of difficult and limited. Sort of the most complicated thing we can sort of do is four-wave mixing and wavelength converting. That's about as complicated as it gets. So it's sort of a dumb technology, but it's very good at transporting data some distance. What I'm going to say here, and some people might disagree with me, is that source and destination routing or wavelength routing is actually sort of inefficient because usually you need to have a large number of transceivers on a single bus just to implement full connectivity. So what we said is, well, we'll use electronics for routing, which we already do with electronic networks on chip. And we're going to use optics or electro-optic devices for switching and optics for transmission. So we'll keep what we know how to do in terms of logic in the electronic domain and then add in our transmission in the optics domain. And so what we come up with is a sort of hybrid circuit switching. So some of you might have seen this sort of thing before because we've been talking about it now for a few years, but I'm just going to go over it briefly just so we're all on the same page. And so the mechanism is actually pretty simple. If we have a core that wants to send data to another core, what it does is send an electronic setup message, which is very small, on this electronic control plane until it gets to the destination core. And as it travels along the electronic control plane, it's sort of reserving resources on the photonic plane up here. So when it gets there, we know that all the photonic resources have been reserved for this end-to-end circuit path. Once it gets there, the destination then sends back another small control message acknowledging that the path is now set up, that the resources are all available, and that the source core can now begin transmitting data up end-to-end on the photonic plane. And here we use wavelength division multiplexing here for high bandwidth. So we use all of the wavelengths in parallel, or all going from one place to another. And we also retain the information on the electronic control plane of which resources are being used in the photonic plane. As you can imagine, if another core wants to now send data to this other core over here, it has to use resources, a path that's already being used. And so what will happen is that the electronic message will get here, and this router knows that this path is already being used, so it will turn it around and send back a path blocked message. And so what we usually do is implement a path retry after a certain amount of backoff. So after a certain amount of time, or random time, this guy will retry this path again. And that's what's known as path contention. And so when the source is done sending all his data, or if he's just done using the path, he then sends down an electronic teardown message, which releases all the optical resources, and then we're good to go. And so this is sort of a way to dynamically set up energy-efficient end-to-end photonic paths on chip. So some of the pros that you can imagine with doing it this way is that, like I said, it's energy efficient. When optics is sort of best used when end-to-end if you don't have to electronically buffer in between. And so we get this end-to-end energy efficiency. It's also high bandwidth, as I mentioned. Doing it this way, we also have the electronic network, which is still available for things like maybe small control messages. I'm thinking synchronization phases between applications, application threads. We have support for things like secure regions, like real things that actually have to be implemented when you're running an operating system. If you want operating system processes to be undisturbed by other threads running in separate regions of your CMP, then we actually have hardware level support for that kind of thing. And the cons you might imagine are, of course, the path setup latency. It takes time for the electronic message to go from one place to another along the chip, setting up the path. And this gets worse when we have higher loads, when more paths are trying to set up, or more cores are trying to set up paths, and also if the paths are longer, they're probably more likely to block because they require more resources. So what I want to talk about briefly is sort of what I'm calling programming and communication, programming model types of things. And what I want to think about, and I don't know all the answers to some of these things, but since these networks are, or what we're trying to think about building these networks for our chips 10 to 15 years down the road, and it's not obvious to me at least what kind of programming models are going to be used for that many cores in sort of a small area. I don't think the problem has been solved even for large computers. If we think about taking large computers and putting them down onto now a single chip, I don't think that problem has been solved well today, and I don't think we know the answer 10 to 15 years from now. Basically, it comes down to the question of how much, what are we going to let the programmer do? How much control does he have over the communication? Can he send variable size messages? And what are the traffic patterns that result of giving the user access to the communication or not? For instance, in shared memory today, basically, all the communication is what I'm calling implicit communication, right? The programmer doesn't know about communication between L1, L2, and memory. He just knows that he wants a memory address, and then it shows up. And so in the exascale report, quote a little sentence that says, shared memory does sort of poorly, pure shared memory does sort of poorly when you scale it up. And this should be fairly obvious. Maybe someone would argue with me, but I don't think so. So if we move to the right towards more explicit communication, or the user knowing more and more about sort of what's going on between cores, this is assuming that cores actually do communicate. So we're talking about dynamic kind of problems where this is actually useful to think about. So PGAS gets a little bit closer, right? Because at least now the compiler knows sort of the difference between a local memory read and a remote memory read. So it's aware that a communication would have to take place depending on which region of memory that it's accessing. And finally, if we take a look at sort of MPI and streaming, MPI were actually a lot of these are scientific application communication patterns. There's already sort of a large code base of MPI stuff for running on very, very large computers, right? Where we have actually relatively larger blocks of data because we can, right? If we have one server that has a lot of data and we can send it to another guy and he'll do the computation on it, that's going to more and more start looking like what's actually just on chip. And finally, if we take a look at streaming, where we have some possibly large amount of input data and a bunch of computation kernels that look like a computation graph, basically, and producing some output data. Would actually look really, really great for sort of this hybrid circuit switching, right? Because what we would do is put this on a core and this on a core and this on a core and set these end-to-end paths optically up ahead of time, and then we just let it run, right? That's a pretty sort of easy problem to solve, this mapping between paths along computation graph and end-to-end optical circuit paths. So for MPI and streaming, we expect I would expect the sort of the hybrid circuit switching idea to be actually a pretty good one. And I think it will definitely play, these two programming sort of ideas will definitely play a fairly large role in at least high-performance computing and high-performance embedded computing, especially. We already see, actually, in the cell processor, there's already 2 programming modes dedicated to these kinds of things. So I definitely think there's room for thinking about this 10 to 15 years down the road. So if we take a look at, I'm going to take a look at some implementation kinds of things. So the electronic plane looks pretty much how you think it would. We have sort of the usual diagram of how an on-chip electronic router looks like, where we have input buffers over here. They make a request of an arbiter who grants them access to a crossbar, basically. And so now the only difference is now the arbiter also controls access to the data switch. In this case, it'll be the photonic plane, the photonic devices over here. And so the arbiter also changes a little bit because now he has to worry about whether paths intersect, right? It's actually just one more step because if you just compute the routing and then you're constrained by the flow control and the crossbar allocation, now you're just additionally constrained by the data switch allocation. And so what we usually assume about our electronic plane is extremely lightweight. We only use one virtual channel, for instance. We don't do any kind of dynamic routing, no fancy flow control. We just use credit-based flow control. So it's very lightweight to save power, and that's sort of the idea, right, is that we don't need this for high bandwidth because we get it from the optics. What I'm calling the network gateway provides access from the cores into both the electronic and the photonic plane. We usually use what's called external concentration as opposed to internal concentration, where basically we want more than one core to share a network access point. So what we do is put more than one core behind an electronic crossbar, which is controlled sort of the same way as a router arbiter by a network interface. We do this instead of internal, if it was internally concentrated, all of these guys would go directly into a photonic switch. And as you might kind of see later, it's actually kind of hard to increase the radix of a photonic switch. And also by doing this, we save on the number of transceivers that we use, since the driver circuits and stuff take up overhead power. So what a core would do is he would make a request to the network interface to send data across the chip. The network interface would use the electronic control plane to set that path up, and it would come back eventually, and he would grant access through the optical transceivers and then out through the optical plane. If we want to talk about the photonic plane, I don't think I need to go into too much detail because we've already seen a few presentations on some of the device stuff. But what we have here, obviously, is WDM putting multiple wavelengths into a single waveguide. And here we show some of the devices that implement that. We can see all the wavelengths measured in a single waveguide here, and we've got some eye diagrams coming out of our lab. One difference in the way we use ring resonators, we're mostly looking at ring resonating technology here. We can see here we have a modulator or a filter that basically, if more than one wavelength is coming into the waveguide, only one of them is resonant with the ring, right? So we've got sort of this kind of a response. And if we put a diode across here, we can inject carriers into it and sort of shift the resonance, right? Well, the same thing applies, except if we make the ring bigger, now sort of this, this resonant mode repeats somewhere, you know, off down here. But if we make it bigger, now it'll repeat sooner. So now what we have are, if all the wavelengths enter here, we can make all of them switch through. So now what we have is a broadband spatial switch, basically, which is analogous to an electronic parallel wire kind of crossbar switch, basically. But now it's just photonic. And so it's the only real difference right here is the diameter of the ring, where this might be 3 microns, and this might be 100, 200 microns, somewhere like that. So again, if we take a look at some of the devices that implement these, we see modulators with shifted resonances, very narrow resonance peak there. We have very low femtojoule per bit modulators with, you know, Sandias, microdisc resonators, usually germanium on silicon detectors with, you know, low picojoule per bit. Getting low. This has been demonstrated, right? But 10 to 15 years from now, we expect it to be much lower. So now if we take a look at those broadband spatial switches, ring resonator-based spatial switches, what we can do is construct higher order switches. So what you see here are 3 different designs for a 4x4 non-blocking switch. And they're going to have different characteristics, right? Here you can see sort of the default path coming in here. If we don't want to switch, goes from left to sort of up. And for this one, it goes left and then turns again and then goes sort of right. And this is going to make a difference for insertion loss, basically. Here you can see one that we had manufactured with ourselves and Cornell, and we tested it, and we showed data coming in through some of the ports. This was done tuning the rings thermally, not electro-optically, and we're still working on getting the rings fast switching with the electro-optic effect. So now if we take some of these sort of different designs, or maybe just one of them for a 4x4, we can scale them up into a larger scale network. A few years ago, our group came out with a design for a photonic torus. You can see the blue sort of rings are the main torus lines, and the red ones are sort of injection and ejection out of those toruses into the gateway. A little later, one of our colleagues came up with a non-blocking photonic torus. It basically uses much more resources, much more waveguide crossings and stuff to basically get non-blocking connectivity out of the network. And then this year we came out with some more sort of topology exploration, basically minimizing insertion loss and minimizing the number of routers and switches in the network. So what we see here is another torus. We call it torus NX for torus no crossings, or at least less crossings, where it's a much simpler design, obviously, than the original photonic torus. And we do that with a modified 4x4 design. And also sort of a wacky topology that we called the square root, again, aimed at minimizing insertion loss. And so now I'm going to sort of talk about 3 of the main sort of characteristics that we think about with designing our photonic networks, and mainly system-level implications of changing the photonic physical layer. So it's insertion loss, noise, and power. And the first is insertion loss. And sort of what the other presenters alluded to is that the number of wavelengths that we sort of inject into our networks can be insertion loss limited. So when we inject light into this waveguide, we can only inject so much power before we see nonlinear effects, before we inject too much power, and that sort of second, third order modes start to generate some signals that we don't want, and which would kind of really increase the the optical loss in our network. On the bottom end, what we see is the detector sensitivity. Obviously, how much power needs to get into the detectors for us to be reliably able to differentiate between a 0 and a 1. And so somewhere in between is the power at which each wavelength is allowed to inject. And they all have to inject at basically the worst case insertion loss that they would experience through the network so that they can get there above the detector sensitivity. And so all of these add up basically to just under the threshold of nonlinear effects. And so the difference is what we call the WDM factor. And so you can see if a network has more insertion loss, basically this would go up, and the sum of these would have to stay the same. So that means we can use less wavelengths, basically. And so sort of qualitatively, as we think about it, as network size increases, basically the number of wavelengths that we can use decreases. And this is sort of for any basically photonic interconnect, right? This isn't just our circuit switch ones. This is for any network designer would have to think about this. And so different topologies might have different sort of insertion loss characteristics, whereas some may be able to use more wavelengths than the others because some experience more or less insertion loss. And we can see that here comparing the 4 different topologies that I mentioned, where the non-blocking torus actually has a pretty significant amount of insertion loss, and so we consider it fairly infeasible, which means that we're going to have to live with a blocking topology until we can do something else about it. If we take a look at the other 2 designs, they have considerably less insertion loss, which actually is still dominated by crossings. We have to sort of engineer when waveguides cross. It's not necessarily easy to do because they have to cross in the same plane, right? And actually, the square root topology gets sort of the lowest insertion loss, which is kind of neat because that's what we designed it for. If we take a look at some of the graphs for the number of wavelength channels that we could use for some of these networks, if we take a look at all the solid lines, the solid lines represent different total optical power budgets depending on the detector sensitivities and the nonlinear threshold. And so again, the square root topology sort of does the best. If we take a look at the dotted lines, this is sort of a game we played where we said if our crossing losses were less, what would the insertion loss be like? Since the crossing loss does dominate most of the insertion loss here, what if each crossing contributed less insertion loss? How many wavelengths would we be able to use then? Actually, the torus X sort of wins out in that case, so that's sort of interesting. And these are the kinds of things that we would really want to be able to do moving into sort of our 10-year, 15-year projection for implementing these networks, really driving sort of research into the devices that we're going to be using here. We're basically saying, hey, give us a crossing that has a lot less insertion loss because we need it. So if we take a look at noise and how that affects the networks, here are basically the 4 different sources of noise that we model in our simulation framework. The first is laser noise, which is actually relatively small. It's quantum noise coming from the laser. And so what we see next is modulation noise coming from imperfect extinction in the modulators. Basically, if we're using amplitude modulation, where a 0 is no light and a 1 is light, then a 0 will still leak light out, and so that contributes some noise when it ends up at the detectors. Next, we have what's called inter-message crosstalk. So if one message is traveling through the network here, and another message is maybe passing by a ring switch that's in the off state, or maybe a waveguide crossing, some of that signal is going to leak into our signal. And so as a message propagates across the network, it's going to sort of accumulate all the sort of inter-message crosstalk that's happening from all the different messages that are out there. And that's going to depend on sort of the engineering that goes on at these crossings, and also sort of the extinction ratio of these rings. And these are all called what's basically called coherent noise, or noise that's at the same frequency as basically the wavelength that we're interested in. Finally, and probably the most important, is intra-message crosstalk, or basically when a bunch of wavelengths all arrive to our detector bank, and we want to filter one of them off. We basically want to filter every single wavelength off and read basically the zeros and ones that they're producing. Because of the imperfect sort of transfer function of this filter, some of the other wavelengths here are going to leak in into our detector. And depending on how closely these are spaced and how many of them, it could be actually a lot of noise leaking into it. And so sort of qualitatively, again, if we consider our optical signal-to-noise ratio versus network size, we can think that if the network gets bigger, then our OSNR is going to go down because we'll have probably more messages interfering with each other. As the number of wavelengths increases, our OSNR is going to go down because of basically because of imperfect filtering. So this is actually kind of weird. As the number of wavelengths or as our bandwidth increases, our OSNR is going to make our bandwidth decrease because we're going to need to either correct for errors or retransmit. So as the bandwidth goes up, the bandwidth goes down. It's kind of interesting. And finally, as our network load goes up, our OSNR is also going to go down because messages are going to start to intersect with each other more. So that's kind of interesting also. And so all these things we need to consider when we actually build a real network, and we can sort of consider both network designs, network gateway designs, and such to sort of get the best out of our optical signals. If we take a look at the simulation results that we did, these are actually kind of preliminary. We have more coming out, hopefully within the next few months. The square root actually does a little bit better than the others, which is completely non-intuitive to me. And it actually almost reaches the point where we consider it error-free. This is 10 to the minus 12, which is considered error-free in telecom. But it's not even there, which means that we definitely need to consider noise and crosstalk as a part, as like heavily integrated into our sort of design methodology, basically. Finally, if we look at power, we've had a lot of talk about energy per bit and power, so I won't belabor this, but we basically have laser power, the active power from, these are gray, you can't see them, shoot. The active power from injecting carriers into the ring to shift its resonance, static power, obviously thermal tuning power, and our transceiver power from drivers and TIAs. If we take a look at the energy per bit that we see between these four topologies, we see that our sort of designs that we optimize for insertion loss are actually a little better, mainly because they have less routers and switches, less electronic resources and stuff, and so they burn a lot less static power, mostly. What Vladimir was talking about with the sort of utilization factor of your photonic links is hugely important, I think. I think it's usually wrong to report your power usage as energy per bit, unless you're talking about the full-scale network for some traffic or some application. So this was kind of nice that we get that added benefit. We were basically optimizing for performance. We wanted to reduce the insertion loss to increase the number of wavelengths. But since we have a simpler design, it also uses less power. If we take a look at sort of the breakdown of power consumption in the networks for the two bad ones, they're actually mostly electronic router logic and router buffer power, which tells me that they're pretty inefficient, inelegant, whatever you want to think. The two newer designs are getting closer to using more of the optical resources, right? And that's what we would want to see. Ideally, we'd want to spend only modulator and only detector power when we really had to. We wouldn't want to dissipate any thermal power, although we're going to have to. And so this is kind of nice. And notice that this is total network power, what you see here, 1.9 watts and 3.2 watts. This was for, I think, an 8x8 network, but what this says is that we can get down to really, really low power, which is why we are really thinking about targeting sort of the high-performance embedded computing, where you'd need really, really, really low power. And I think these were up around 4, and oh, this was around 2 watts, but that's not normalized, so don't worry about it. If we take a look briefly at performance, we ran some simulations. Our simulator is called Phoenix Sim, by the way. It was published in date this year. It's available on our website in beta. Hopefully, we will have a new version released soon, which fixes some of the bugs. So you could go download it and run these simulations yourself if you wanted to. If we take a look at a photonic mesh versus a packet switch electronic mesh, we see some of the things that we would basically expect. We see 3 different message sizes here, and this is for uniform random traffic. We run all sorts of different synthetic traffic, but this is pretty typical of what we see. So for a 32-byte message, which is pretty small, it's maybe a control message or maybe a small cache line. What we see is both higher zero-load latency. This is latency versus measured bandwidth. We see higher zero-load latency, which we're going to see throughout message sizes probably, except for very large ones. And it also doesn't get the same amount of bandwidth as the electronic packet switch one does. And this is purely just in the overhead of setting up the end-to-end path, right? If we take time to set up this end-to-end path, we better have enough data basically to send along it, or else it's not going to be worth it. At least for random traffic, and random traffic is all willy-nilly across the chip. If we have something more organized, which maybe user controls or some automatic arbitration controls, then it will definitely get better. But as we increase message size, then the photonic mesh suddenly becomes worth it to set up this end-to-end path. And we see this crossover point at probably a little under 1 kilobyte, maybe 0.8 kilobytes. And then again, for very, very large messages, our zero-load latency is an order of magnitude better than the electronic mesh. And you would expect that. And most people would say, we're never going to see 32 kilobyte messages on chip. But in 15 years, you might. I don't know. We also ran some scientific application traces. These are mostly MPI-based. And we actually usually have a difficult time finding really good traces for on-chip communication, mostly because they're all shared memory and pure shared memory type, right? Not all of them, obviously. Someone would tell me that they have, they know of plenty of MPI-based traffic, but we're always looking for more so we can investigate some of these cool trade-offs that we see with circuit switch networks. If we take a look at the execution time, here up is better. These are smaller than these. This is log scale. Our photonic mesh does a good 2 to 3 times better than the electronic mesh for Cactus and GTC, which are sort of a relatively small number of large messages. That's what we'd sort of expect. MadBench, they're sort of basically equivalent because MadBench actually has a large number of application phases which need to be synchronized. Here, the photonic mesh actually does use its electronic network, its electronic control layer for the synchronization messages that happen between application phases. So at least it's using it for something other than path setup. For Paratech, however, Paratech is a large number of small messages, and so what you'd expect is that photonic mesh can't amortize the overhead of setting up its path. And so that's exactly what you see, 1.5 orders of magnitude worse execution time, which is interesting. And this is pure circuit switching. We've come up with a few methods basically to make this better, but I think it's interesting to look at just the pure cases. So you can see the trade-offs between circuit switching and packet switching or arbitration schemes or whatever. If we take a look at the energy, it's sort of the same story for Cactus and GTC. We get basically an order of magnitude better energy consumption for also MadBench too. And for Paratech, it's actually worse because since we're blocking so much by setting up these paths, it sits there burning both static power. Actually, most of it is static power since it does take so much longer. We just burn more energy. And also, having to retransmit these path setup messages does take dynamic power out of the electronic network. So finally, I'm going to talk about just quickly some other interesting issues and forward-thinking things that we have already thought about. The first one, of course, being memory access. How do you get data in and off of the chip from DRAM? And so I have a paper coming out in November in supercomputing that I hope you'll take a look at. And basically what we say is that if we have this on-chip sort of mesh, all we have to do is put memory access points on the periphery, which enable us to go from any core on the network to a circuit, basically off the chip edge to DRAM. And what we do is we bandwidth match what we can get on chip to sort of parallel DRAM chips feeding into this optical circuit. And what we also get is that the memory controller logic is hugely simplified. Basically, what the memory controller, all it has to do is worry about row access, column access time. And it doesn't have to worry about optimally scheduling all these small accesses into one sort of DIMM to be able to get utilization out of it. All it has to do is worry about managing the contention between circuits requesting access to it. And so that's going to be kind of interesting. And actually what we see is for high-performance embedded applications, we get pretty significant speed up, which was a surprise to me, believe it or not. Some of the work that I presented at Hot Interconnects that some of you may have seen was actually removing the electronic control layer and having sort of distributed but synchronous switch controllers and gateways to set up the photonic switches using time division multiplexing. And this was aimed at providing fairness to the sort of path setup mechanism, which the electronic control layer right now can't provide by using its sort of dynamic path setup, path block mechanism. So I also have a paper coming out that's an extension to this in Journal of Parallel and Distributed Computing in January. That should be pretty interesting, I think. Finally, what we have is sort of increasing the wavelength granularity. Right now, what we're working with is a broadband ring where we can switch the resonance of sort of all of the wavelengths, so we get basically a broadband switch. But if we engineer the rings sort of a little differently, what we can get is that if all the wavelengths are coming in, we can sort of select maybe half of them at a time. There we go. We can select half of them with one ring, or we can select all of them with both rings. Let's see. Yeah, so we can select all of them with both rings, half of them with one, or the other half with the other ring. And so we can sort of try and increase the number of these rings to get sort of more granularity in the paths that we can establish. And this actually is not straightforward to do it. You don't just have the diameter or anything like that, mostly because the way that these resonant modes repeat doesn't stay the same as we sort of change the diameter of the ring. So it's actually kind of a hard problem that we'll probably sort of need to use software to sort of optimize the way that we do this. And so in conclusion, I definitely think the programming and application communication model is going to play a large part in how we design the photonic networks, because I think photonics is coming. And so I don't think you can think about how to design a photonic network without thinking about what area of computing you're in and how much control the user has over the communications that happen and how that's going to affect message size and traffic and all sorts of good things. So I think it's definitely an interesting sort of solution. Hopefully I'm not just searching for a problem to my solution. I think it definitely does warrant investigation. And so we do have plenty of interesting trade-offs and an interesting design space here for the photonic physical layout, basically, and the photonic devices, where we get system-level benefits from basically small things like improving crossing loss will give you huge gains in insertion loss. And also some network-level arbitration, switching, routing improvements. So that's it. Thank you. Thanks.
Any questions while we switch speakers? If not, I'd like to introduce the last speaker for the day, Dr. Frankie Liu, who is a circuit designer at Sun Labs Oracle. Frankie's background includes some years at Applied Materials doing device physics research, as well as building CERDES at True Circuits. Frankie did his PhD at Stanford, and in fact, we were undergraduates at the same time, and freshman year lived about 200 yards apart. Little did I know that a quarter century later, I'd be asking him to give a talk on circuits. So He's going to talk about some of the issues when you go from the electronics to the optics and back. You have to start and end with sand, and this is what he's going to talk about. Thanks.
You have heard a lot about wide consider optics. In this presentation, I'll talk a little bit about the costs involved from a circuit design perspective. In particular, what is shown here is just a very simple diagram of a transmitter and receiver part of the link, the top being the transmitter, bottom being the receiver. The transmitter, some bits coming in, some muxing going on, some timing going on, retiming. Those bits gets converted to some signal conditioning before they get converted to optical. The optical goes across a waveguide, gets converted again to electrical, and that is again amplified before it becomes digital bits out. Some demuxing and timing going on, and bits coming out. I will focus primarily on this blue sections here, because as you heard, these are the ones that consume a lot of power. Jack has mentioned about, this is an example slide of where you have this link-to-link connections between two chips in a microchip model. And in each one of these connections would be the transmit and receive system that was shown on the previous slide. What makes some interesting design choices here from a circuit perspective is that if you require, for example, some synchrony between these chips, for example, during calibration, that might be possible if you share a slow clock among these or some slow signals to indicate when to calibrate the receiver and transmitter. I'd like to focus now on the driver side of things. And part B, I'll focus on the receiver side of things. Basically, the signal conditioning is fairly simple. You convert the bits into, in this case, a modulation in current and or charge, if you will. And that gets converted by the electrical optical interface into a modulation in the amplitude of the optical signal, or if you will, the number of photons is modulated by the electrical signal. There are device flavors that you heard already, either with VCSEL LEDs or something that has a remote light source, in which case you have rings, quantum wells to modulate that light source. I will consider in particular rings, and you heard from the previous talk, rings are basically resonant structures, meaning that there's a particular frequency which is, or I should say, there are modes within that ring which resonate. And as you vary, say, the path length by some electrical means, then you change the resonance frequency, and the original source that you had then does not resonate, does not go into the ring. Now, from a circuit design perspective, a ring modulator can be just abstracted as a lumped capacitance, because all that I'm doing is changing the index of refraction, and to do that, I inject electrons in or take some out, and that will change the index of refraction. So it's a fairly simple abstraction. Unfortunately, they require high voltage in order to create enough index of refraction change. And that means that I need to go typically 2 to 3 volts in order to get enough carrier contrast. And that means that if I want to operate at high speeds, I still would need some low voltage devices. But because of the high voltage that's required in order to drive the modulator, I would have to create some supporting circuitry to protect such that each of these devices does not see more than a voltage difference between its terminals. But let me explain here briefly. So this is basically a path, say, to a high voltage, so dumping some charge in, and then this dumping some charge out. Okay, so it's a typical thing. The only reason why they're stacked is because, again, I want to protect each of these devices. They're low voltage devices for fast speed, but they cannot see a large voltage change. The modulators themselves, because they see temperature and aging effects, will require additional circuitry to control the environment of the modulator. And that is actually a significant cost in terms of the energy, in particular because they're very sensitive. You have to keep the temperature to, sub 1 degree. And the standard solutions to dynamically heat them and to heat them, you heard the static power dissipation there. The question is whether or not such heating really makes this solution efficient or feasible. And at least I haven't seen it as being at scale, whether this is practical yet or not. Okay, I'll switch gears here and talk about the receiver side of things. You've seen this picture before, but now this optical amplitude variation through the optical electric converter will be converted into some current. This here is a photodiode. It receives some photons, generates electron hole pair, and those there's a typical number associated with that. They call the responsivity of the photodiode. Basically, the number saying how much current is generated per watt that's impinged on the device. And here's a typical number, 1 microamps per microwatt. This current then, in order to be useful, has to be converted to some voltage because eventually it will become a digital signal out. This is what the job of, this is a very simple receiver, say. This current gets converted to voltage as it flows through this resistor. This CD here, that's an important parameter. So it is the parasitic capacitance. In this case, the let me put a line here. So you can think of this part as sitting in some other substrate, say silicon germanium. And here is where you want your digital signal out sitting in CMOS. So they're connected by some bonding in between them. And that connection introduces some parasitic capacitance. It's not something that you really want because not desirable, but it exists because you need to have the connection in between. Because you will see that this capacitance introduces a low-pass filter to this particular receiver. From your Circuits 101, you know that the RC system has a bandwidth of 1 over RC. The effect, if you, for example, wanted to end the 3 dB point, this is a plot of the frequency response of a simple RC, 3 dB point being at the 1 over RC. If you wanted to increase the bandwidth, say, then say by a factor of 2, that is move the 3D point, you will incur a cost in the gain. So the gain, RL, go down by a factor of 2. So there's a typical bandwidth to gain trade-off. Now let's talk about the noise associated with this particular receiver. We already mentioned about the bandwidth, 1 over RC. The gain, simple R, the current goes to the resistor, gets converted to a voltage. The noise here is purely dictated by the capacitance on this node, KT over C. If you just write a simple expression for the SNR here, this is a current, photo-generated current. This is a voltage, or voltage squared. And this is the mean square of the voltage fluctuation. And the signal-to-noise ratio, then, if you re-express this in terms of the bandwidth, you will see that the RL has pretty much disappeared, and the SNR for fixed bandwidth and capacitance, there's very little room to play, pretty much, because the CD is fixed by the parasitic of what connects in between your photodetector and your other substrate, and the bandwidth is what you desire. So this equation is what I want to imprint on your minds, is that there's very fundamental trade-offs here. That is, if I want to increase my bandwidth by a factor of 2, I either have to decrease this capacitance by a factor of 4 or increase the current by a factor of 2. Sorry, it's not moving here. I don't know. Where should I step into the box? Okay. Okay. Page. Okay.
How many engineers does it take to advance a slide? The answer is more than 2. Hang on. Nope.
Okay, I'll just use the arrow keys, sorry. Why are we interested in SNR? Because it directly correlates with the probability of error. So that is, for a larger SNR, you have smaller probability of error. And here I just, again, just want to have a very simple formula for you guys. That is, take a SNR number, divide it by 4 or 5, and that roughly gives you the probability of error. So 80 divided by 4, around 10 to the minus 20 probability of error. And this shaded region here is the region of interchip communication. So we want to roughly shoot for SNR between, say, 80 and 50 or so. So going back to the example here, let's pick some numbers. So for a bandwidth, say, of 4 gigahertz, and it's a typical number for the parasitic capacitance, and this corresponds to 10 microwatts of optical power, you get this humongous number, right? So no problems in probability of error. You have so much room. So what's the catch? The catch here is that the small signal from the previous example for that current corresponds to an 8 millivolt signal. And you really want, at the end of the day, something that's closer to a volt. In order to do that, you have to go through some stages of amplification. And these stages of amplification will introduce noise and thus degrade your SNR. Recall from that simple example that there was a very tight coupling between the bandwidth and the gain. That is, if I wanted to increase the gain, I would degrade in my bandwidth. And in particular here, I already mentioned from the example that you correspond to 800 ohms and 10 ohms, 10 microamps, so 8 millivolt signal. But what if we wanted more gain? And how do we decouple the gain and bandwidth trade-off? Here's a simple topology that is often used. And in this case here, it's a transimpedance amplifier. Basically, the resistance, the input resistance that is seen is divided by a factor of 8. So RF sets a gain, as previously, so IN times RF, sort of your gain. But towards the bandwidth, it sees a reduced R because of the feedback through this loop. So you can think that for a fixed bandwidth, that is, if I fix my bandwidth as previously, I can effectively increase this R by a factor of A and see an increase in gain. So they're still tightly coupled. The only difference is that I have added a factor of A in there. What happens to the SNR in this case? Well, here's our friend, which I would like you to remember. Okay. That has not changed very much in terms of the SNR. And here is, I just put some arbitrary function. I'll show you later what that looks like. That depends on certain tuning knobs of this circuit here. Okay. So Cm here is, I just say, is a parameter to indicate the size of the input stage. Okay, so input capacitance, if you will. CD you already know. So this function here only depends on the ratio between these two. And here is the bandwidth and omega t. Omega t is a technology parameter. So that corresponds to the gain bandwidth product of 1. So for higher technologies, this would be a larger number. Okay. The point here is that if you want to just get some simple estimates for SNR, get somebody's design point for SNR, whatever they have, and if you want to project forward, say, what happens if I want to increase the bandwidth by 2? I hope that you can still use this to project what will happen to the SNR. That is, and what you need to do to the other parameters in case you want to maintain the SNR. Okay. And I would like to propose that this is secondary importance, but I will show you what its effect is. So that function f for the TIA topology looks something like this. So recall that there is the parameter Cm over Cd, which is the ratio of the device capacitance to the parasitic capacitance. And here are just plots for different technology nodes. Okay, so the larger technology nodes, you get slightly improvement in SNR. Sorry, this axis here is SNR. So if you recall the number that we had previously for the simple resistor receiver, we had SNR of 750, huge, right? So we have decreased maybe by a factor of 2.5 to 3 over here, simply by having that additional amplifier. Now, one may choose to operate here at the optimum SNR. And that optimum point for the transimpedance amplifier is about a ratio square root of 2. So that's the ratio between the input amplifier to the parasitic capacitance. In this end over here, the SNR falls off because the input capacitance becomes a significant portion of the parasitic capacitance. And as you recall, the total capacitance of that node determines the bandwidth. So if you wanted to have the same bandwidth, you need to reduce R, which actually introduces more noise. So that's why on this side, it's falling off. On this side, on the other hand, Cm, that is the amplifier's capacitance, becomes a smaller portion of the diode capacitance. So the bandwidth is pretty much determined by the diode capacitance. It falls off over here because as the device gets smaller, it actually introduces more noise. Now, the question is here in terms of what we're really interested in is to maintain a particular SNR. That is, if we should remember those numbers from the probability of error, somewhere about 80 to 50, somewhere in here. Okay, that gives us the probability of error that we want. So that implies that if I want to shoot for that, I would not want to be here on the optimum SNR position. Why? Because this implies a large Cm, let's say around, remember the 1 over square root of 2. And that means that I burn more power over here. Since I'm shooting for this particular SNR, I can actually burn less power by going to a smaller ratio between the amplifier capacitance to the diode capacitance. This is just rephrased over here. That is, that ratio between the input capacitance of this amplifier to the diode capacitance can be converted, is pretty much a proxy for power. Here's some typical numbers. So that's a ratio. This is a capacitance, parasitic capacitance. These are typical numbers, just converting gate lengths to femtofarads and how much current per micron of gate length. This number increases slightly per technology node, and this is just the working voltage. And again, you need a design point to begin to use that SNR equation that I have. And here's a design point here. So for 4 gigabits, same as before, and you're shooting for SNR of 50, going through this over here gives you around 200 femtojoules per bit. So the bottom line here is that the TX and RX circuits consume about 2/3 of the optical link energy, about 1/3 each. So they're a large fraction, but as you've seen through this presentation, in the TX side, one of the more worrisome parts is really that control of the environment of your modulator, for example. And on the RX side, given that you have a fixed probability error that you're trying to target, that fixes your SNR, and that there are very fundamental trade-offs between the bandwidth, signal, input capacitance, and that equation that I showed you, inversely proportional to the square of the bandwidth and of the diode capacitance. That hopefully will stick on your mind, because that shows you what you need to do in order to maintain the SNR as you push the bandwidth and so forth. And just some references. So ring modulators, some detectors, and some of the work that we have shown for that 200 femtojoules per bit.